Here's a region bounded by y equals to 4 minus x squared and the x-axis. If you have a constant density, here, usually in physics, density is mass divided by volume, right? But here we're going to use surface density, and that's for objects that are very thin. That if you have an object that's very thin and you don't really want to think about the thickness, you can divide the mass by the area, and that's called the surface density. Usually you use rho for volumetric density that people are more used to, but there are other types of density too. There's the linear density when you have a very thin wire, and there's also the superficial density, sigma. Okay, so this is a very thin, flat object. So let's say you have an object like that, and you have a density function that's given by y. In other words, when you're here, that's when y is 0, right? So over here, there's almost nothing. Okay, but up here, when y is 4, this is much more dense than things in here. So as you go up, more things, more stuff is there. Like there's more concentration of materials as you go up. Okay? So see, this side is longer, but this is almost weightless because density is almost 0. Whereas this side is kind of small, but if you have this much, it's probably heavier than this one. Okay? So you can kind of have an idea of what this object is like. And if you wanted to know the total mass of the lamina, how would you find it? Well, if you simply had the constant density, then all you have to do is find the area and multiply that density. That's all you have to do. So for example, if this was not y, it was say 5, then all you have to do is find the area under the graph, and that's even just done by Calc 1 stuff. It's just integrate from -2 to 2 dx. That gives you the area, right? And then you multiply 5 to that, and that will be the entire mass if sigma was exactly equal to 5. But unfortunately, we can't do that here because the density varies from point to point. So instead of that, what we need to do is we need to think of sigma is mass over area. Okay, so this is saying that if you take a very small portion of this object, then there are two quantities attached to this. There's the mass of this small area. There's this mass, but there's also the area itself, right? And because the surface density means mass divided by the area, you just divide dm by dA, that's your sigma, okay? Which means that dm is sigma times dA. Okay. And that allows us to figure out the entire mass by doing a double interval. So let me try to explain that point. But what I'm about to write is universal. This appears in so many different places, which is the whole is sum of its parts. Okay? Does that make sense? If you divide this into many small things, tiny little things, right? And then you add them up, you recover the whole. The whole is sum of its parts. Does that make sense? Now, how many of you are taking physics 2 right now? Yeah. If you read your physics textbook, I wonder if you do, but it's a good thing to do. Try reading your textbook. Sometimes you gain insights that the classes don't give you. So if you do, you'll see several calculations that look exactly like this. Yeah, mass is sum of its parts. Okay, so we can do that, and then we will be adding these small parts over this region, so we're doing a double integral over this region. That's what's happening. Okay, let's continue on. Now we learned that double integrals, you have to make a choice whether to paint right or up. For us, it's easy to go up because this bound is simply y equals to 0, and this bound is y equals to 4 minus x squared, so it makes more sense to go up. If you go upwards, that's going to give you 0 and 4 minus x squared. Okay? I said that it's curve to curve, right? The bottom boundary is this one, which is y equals to 0. And then as you paint up, the top boundary is this one, which is y equals 4 minus x squared. And I've simply put those two functions down there. And even if I didn't write down y, you should really think of 0 as y equals to 0, which is the horizontal line, the x-axis. And you should really think of 4 minus x squared as y equals 4 minus x squared, which is this parabola. Good? And then once you integrate out, what happens? Everything gets flattened and added onto the x-axis, right? On the x-axis, what are the bounds of the x values?
The zeros?
No, the y coordinates are 0, I agree. But then if you flatten it out and place all the integrated values on the x-axis, the value of x goes from where to where? Negative 2 to 2. Yes, that's correct. So negative 2 to 2. Okay? And then, because, and then dm is sigma dA, right? So we're going to put sigma dA sigma is y, and dA, if I'm painting upwards, should it be dx dy or dy dx? dy dx, yes, because painting upwards means you're increasing in the y direction, right? So it's dy dx. And that gives you 1/2 y squared. You're plugging in 4 minus x squared and 0 dx, negative 2 to 2, which if you pull the 1/2 outside and if you plug this in here, I'll skip some of the calculations because it's kind of straightforward. It's going to be x to the 4th minus 8x squared plus 16 dx. And see, these are all even functions. What's an even function? If you draw the,
Looks the same on both sides of it.
Yeah, so if you draw the graph of x to the 4th, it's like that. So the left and right have the same exact graph. That's called an even function. Why is that important? That's because you can save time of calculation by only integrating from 0 to 2 rather than negative 2 to 2, but double that result. So for example, if you had, here's x to the 4th graph, and you wanted to integrate from negative 2 to 2, well, integration from negative 2 to 2 of x to the 4th dx is going to be the same thing as twice of integration from 0 to 2 of x to the 4th dx. Don't you agree? Because this much will be this area, right? And then if you double that, you get the entire area without having to plug in negative 2. The reason we like this trick is because plugging in negative 2 is nasty, whereas if you plug in 0, it's so easy. Yeah. So let's do that. We're going to change the integral from -2 to 2 to 0 to 2, and you're going to double it, but times 2 is going to cancel the 1/2, okay? And you end up with this. Whose integral is 1/5 x to the 5th minus 8/3 x to the 3rd plus 16x, and then you plug in 2 and 0. That's 32 over 5 minus 64 over 3 plus 32. And if you put everything over 15, oh, that's a challenge. Let's see. 396 minus 320 plus what's that? 480, and then that's 160. That's 160 plus 256. Huh, okay, interesting. Well, that's what you get. That's the mass of this object.